26 light-years from Earth, a telescope spotted something that shouldn't exist. Water vapor on a planet where the surface melts metal. Scientists are stunned because this rocky world named GJ486b orbits so close to its star that a year there lasts only 36 hours. Temperatures reach 800 degrees F. No atmosphere should survive. Yet the James Webb Space Telescope detected water's signature in infrared light filtering through this alien world. But here's the twist that has astronomers arguing. The water might not be on the planet at all. It could be hiding in cool spots on the star itself, a cosmic mirage that would shatter what appeared to be the first atmosphere ever found on a rocky planet beyond our solar system. The signal appeared on screens at the Space Telescope Science Institute like a whisper from another world. Scientists had pointed humanity's most powerful eye at a rocky planet 26 light-years away, expecting to find nothing. Instead, they found water vapor. The discovery sent shockwaves through the astronomical community because water vapor should not exist where they found it. This wasn't a gas giant like Jupiter, where finding water is common. This was a rocky super-Earth, and if the signal is real, it would mark the first time anyone has ever detected an atmosphere on a rocky planet outside our solar system. The telescope had been watching GJ486b as it crossed in front of its star twice. Each transit lasted about an hour. During those precious minutes, starlight filtered through the upper layers of the planet. That light carried fingerprints, chemical signatures. Buried in those signatures was the unmistakable mark of water molecules absorbing specific wavelengths of infrared light. 3 separate teams analyzed the data using 3 different methods. All 3 reached the same conclusion: water vapor. But here's where the story takes a strange turn. The water might not be on the planet at all. Red dwarf stars, the type this planet orbits, are covered in dark spots similar to sunspots. These star spots are cooler than the surrounding stellar surface. Much cooler. Cool enough that water vapor can exist there, floating in the star's atmosphere rather than the planet's. The researchers ran computer models comparing both scenarios. A planet with a water-rich atmosphere produced one signature. Star spots with water vapor produced another. The signatures were nearly identical. Sarah Moran from the University of Arizona, who led the study, put it bluntly: "We see a signal, and it's almost certainly due to water, but we can't tell yet if that water is part of the planet's atmosphere or if we're just seeing a water signature coming from the star." The uncertainty is maddening. For decades, scientists have hunted for atmospheres on rocky exoplanets. They found them on gas giants. They found them on hot Jupiters. But never on a world like this. Never on a planet that resembles Earth in composition, even if it resembles hell in temperature. The stakes couldn't be higher. If this planet has an atmosphere, it would prove that rocky worlds can hold onto their air even in the harshest environments imaginable. And if a planet this close to its star, this scorched, this bombarded by radiation, can maintain an atmosphere, then what about the billions of cooler, calmer worlds orbiting habitable zones across the galaxy? Imagine taking Earth and squeezing it until it weighs 3 times as much while only growing 30% larger. That's GJ486b. The gravity on this world would crush you. Your weight would triple. This is what astronomers call a super-Earth, a rocky planet more massive than our home, but smaller than Neptune and Uranus. Scientists confirmed its existence in 2021 after spotting the telltale dimming of its star as the planet passed in front. The planet sits in the constellation Virgo, visible from Earth's northern hemisphere during spring months. But GJ486b is nothing like the gentle maiden that constellation represents. This world is a furnace. Its surface temperature hovers around 800 degrees F, hot enough to melt lead and zinc. The planet's density tells us it's made of iron and rock, similar to Earth's composition. But any resemblance ends there. The world completes one full orbit in just under 1.5 Earth days. A year on this planet is shorter than a weekend on ours. The planet races around its star at blistering speed, locked in a tight embrace that brings it dangerously close to the stellar surface. But there's something even stranger about this world. The planet doesn't rotate the way Earth does. Instead, GJ486b is almost certainly tidally locked. One hemisphere faces the star eternally, baking under constant radiation. The other hemisphere faces the void of space, frozen in perpetual darkness. 26 light-years. That number sounds vast until you understand what it really means. 1 light-year equals about 6 trillion miles, the distance light travels in a full year. Multiply that by 26 and you get the distance to GJ486b. In cosmic terms, this planet practically lives in our backyard. Our Milky Way galaxy spans 100,000 light-years from edge to edge. The star it orbits, GJ486, is what astronomers call an M dwarf or red dwarf star. These stars are the most common type in the universe, making up about 70% of all stars. They're small, cool, and dim compared to our Sun. GJ486 has only about 30% of the Sun's mass and shines, with less than 2% of the Sun's luminosity. Because the star is so dim, a planet needs to orbit extremely close to receive enough warmth for liquid water. GJ486b orbits even closer than that habitable zone, which is why it's so scorchingly hot. But the closeness has an advantage for scientists. The nearer a planet is to its star, the more starlight filters through its atmosphere during transits. The stronger the signal, the easier the detection. Red dwarf stars are monsters disguised as weaklings. They burn dim and cool compared to stars like our Sun, but they live violently. These stars unleash devastating flares, massive bursts of X-ray, and ultraviolet radiation that blast any nearby planets. The flares can increase a star's brightness by 10 to 100 times in just minutes. The violence gets worse when red dwarfs are young. During their first billion years, these stars throw stellar tantrums constantly. High-energy radiation bombards their planets day after day. Any atmosphere that forms gets torn away molecule by molecule. The ultraviolet light breaks apart water into hydrogen and oxygen. The hydrogen escapes into space. The oxygen either escapes or reacts with surface rock. Either way, the atmosphere vanishes. GJ486 is billions of years old now, past its most violent youth, but the damage may already be done. That's why finding an atmosphere on GJ486b would be so shocking. The planet should be airless, stripped bare, a dead rock circling a dying ember. Red dwarfs have another trick. They live forever. Well, not literally forever, but close enough that the difference doesn't matter. A star like our Sun will burn for about 10 billion years total. Red dwarfs can burn for 10 trillion years. That's 1,000 times longer. The universe itself is only about 14 billion years old, which means no red dwarf has ever died of old age. This longevity creates an interesting possibility. If rocky planets around red dwarfs can somehow keep or rebuild their atmospheres despite the radiation, they have trillions of years to develop life. That's why scientists care so much about whether GJ486b has an atmosphere. It's not about this one planet. It's about the billions of rocky worlds orbiting red dwarfs throughout the galaxy. A year on GJ486b lasts 36 hours. While you sleep through 2 Earth nights, this planet completes an entire journey around its star. The planet tears through space at roughly 200,000 mph. At that speed, you could travel from New York to Los Angeles in about 80 seconds. There are no seasons on this world, no slow progression from summer to winter. If humans somehow survived there, they would celebrate a birthday every 36 hours. A teenager would be 3,000 years old in Earth years. From the dayside surface, the red dwarf would loom about 15 times wider than our Sun appears from Earth. It would cover a huge portion of the sky, a vast crimson disk burning silently above. Scientists can calculate the orbit precisely by measuring how often the planet transits its star. Every time GJ486b passes in front of its star, the star dims slightly. That dimming follows a predictable pattern, every 1.467 days like clockwork. Imagine a world where the Sun never moves. It hangs frozen in one spot in the sky forever, never rising, never setting. That's the dayside of GJ486b. Now imagine standing on the opposite hemisphere where the Sun never appears at all. Total darkness, perpetual night. That's the night side. Between these two extremes runs a narrow band called the terminator, where the star sits permanently on the horizon, casting eternal twilight across an alien landscape. Tidal locking happens when a planet orbits close enough to its star that gravity pulls differently on the near side versus the far side. Over millions of years, this gravitational gradient acts like a brake on the planet's rotation. The planet slows down and eventually stops rotating altogether relative to its star. The dayside temperature reaches 800 degrees F, but the nightside could be hundreds of degrees colder, maybe even close to absolute zero, depending on whether an atmosphere exists to transport heat. If there's no air, the night side becomes a frozen wasteland, where even gases like carbon dioxide freeze solid. If an atmosphere exists, it changes everything about tidal locking. Air flows from high pressure to low pressure. The dayside, being heated constantly, would have rising air and lower pressure at the surface. The night side, being cold, would have sinking air and higher pressure. This difference would drive winds howling from night to day at supersonic speeds, carrying heat from the scorched hemisphere to the frozen one. 800 degrees F, let that number sink in. At 450 degrees, paper ignites. At 621 degrees, lead melts into liquid. At 786 degrees, zinc melts. This planet's surface exceeds all of those thresholds. The ground would glow dull red from its own heat. Any water that somehow reached the surface would flash into steam instantly. This heat creates an interesting problem for the water vapor hypothesis. If water exists in the planet's atmosphere, where did it come from? The planet is far too hot for liquid water on the surface. Any primordial water would have been lost billions of years ago. For water vapor to exist now, it would need a continuous source. The only plausible source is volcanic activity, releasing steam from the planet's interior. Deep below the surface, pockets of water could exist as superheated liquid or steam, held in place by immense pressure. Volcanic eruptions would blast this steam into the atmosphere, temporarily replenishing it. That's the competing explanation that keeps scientists up at night. Just like our sun develops sunspots, red dwarf stars develop star spots too. But red dwarf star spots are different. They're cooler, much cooler. The star's surface might be 6,000 degrees, but a star spot could be 4,000 degrees or less. That temperature difference matters because of water. Water molecules break apart at high temperatures, splitting into hydrogen and oxygen. But at lower temperatures, water can exist as vapor. Our sun is too hot for water vapor in sunspots, but cooler red dwarf stars can harbor water in their star spots. When the planet crosses a star spot during transit, the light filtering through the planet's potential atmosphere also carries the signature of the star spot. The two signals mix. Separating them becomes nearly impossible with current techniques. The researchers ran computer models simulating both scenarios. One model placed water in the planet's atmosphere. The other placed water in star spots. Both models produced transmission spectra that matched the telescope's observations almost equally well. That's why scientists need additional observations with a different instrument called NIRS-SPEC, which can observe at shorter wavelengths. NIRS-SPEC could potentially see the divergence between the two models. If the water signal strengthens at shorter wavelengths, it's probably from the star. If it weakens or disappears, it's probably from the planet. But those observations haven't been completed yet. Adding to the confusion, red dwarf stars like GJ486 are magnetically active. They're covered in star spots. Some cover 10% or more of the star's surface. When a planet transits such a star, it's almost guaranteed to pass in front of at least one star spot during the hour-long transit. Light tells stories. Every time a photon passes through a gas, certain wavelengths get absorbed while others pass through unaffected. The pattern of absorption creates a unique fingerprint for each molecule. Water absorbs strongly at specific infrared wavelengths. Carbon dioxide absorbs at different wavelengths. Methane has its own signature. By spreading starlight into a rainbow spectrum, and measuring which colors are missing, scientists can read the chemical composition of distant atmospheres without ever visiting them. This technique is called transmission spectroscopy. The telescope observed GJ486b during two separate transits to confirm the signal. The first transit showed the water absorption feature. The second transit showed it again. The consistency meant the signal was real, not just noise or instrument error. The spectrum came back mostly flat, meaning the planet's atmosphere blocks about the same amount of light at most wavelengths. But at the shortest wavelengths, around 1 micron, there was a rise, a bump in the data. That bump matched the wavelength where water vapor absorbs light. 3 separate research teams analyzed the data independently using different statistical methods. All 3 reached the same conclusion. The most likely explanation for the bump is water vapor. But all 3 also acknowledged that star spots could explain it equally well. Multiple observations also help average out noise. The 2 transits occurred months apart. If star spots are causing the signal, the spots might have rotated to different positions on the star between observations. If the water signal came from a specific star spot, and that star spot rotated out of view between transits, the signal might disappear or change. But it didn't change. That could mean the water is in the planet's atmosphere after all. Or it could mean the star is covered in so many star spots that the planet always passes in front of at least one. But then came a twist. August 24, 2024, a new scientific paper dropped like a bomb on the GJ486b debate. The title was blunt: "No thick atmosphere on the terrestrial exoplanet GJ486b." The paper presented results from 2 additional telescope observations using a different technique called secondary eclipse spectroscopy. Instead of watching the planet transit in front of the star, the observations measured what happened when the planet passed behind the star. The conclusion challenged everything the earlier transmission spectroscopy suggested. When the planet goes behind the star, the system's total brightness drops slightly because we lose the planet's thermal emission. By measuring how much the brightness drops at different wavelengths, scientists can determine the planet's dayside temperature and look for emission features from the atmosphere. The new observations showed neither. The team measured the planet's dayside temperature at 865 degrees F, give or take 14 degrees. They compared it to the maximum expected temperature for an airless bare rock with no heat redistribution. The measured temperature was 97% of the maximum. That ratio suggests the planet redistributes heat very poorly, if at all. A thick atmosphere would transport heat from day to night, cooling the dayside and warming the nightside. But GJ486b's dayside temperature is almost exactly what you'd expect for bare rock. The paper concluded that the planet either has no atmosphere or possibly a very thin one with less than 1% water vapor. This result directly contradicts the water vapor detection from transmission spectroscopy. How can both be true? The answer might lie in the different techniques' sensitivities. Transmission spectroscopy looks at starlight filtering through the very top of the atmosphere, the highest, thinnest layers. Secondary eclipse spectroscopy looks at thermal emission from the entire dayside, sampling deeper layers. It's possible the planet has a very thin, high-altitude layer of water vapor that transmission spectroscopy detected, but not enough atmosphere to significantly affect heat transport. Alternatively, the transmission spectroscopy might have detected stellar water vapor in star spots rather than planetary water vapor. The August 2024 paper represents the scientific process working as intended. One team reports a detection. Another team tests it with a different method. The results disagree. Now scientists must figure out which result is correct, or whether both are correct but measure different things. When scientists say GJ486b might be airless, they mean an atmosphere so thin it barely matters. Atmospheric pressure on Earth at sea level is about 14.7 pounds per square inch. Venus has surface pressure 90 times Earth's. Mars falls between these extremes with surface pressure only about 0.6% of Earth's. GJ486b might have something far thinner. Imagine atmospheric pressure 110 of Mars, or 1100, or 11000. At some point, calling it an atmosphere becomes misleading. It's more like a thin haze of molecules occasionally bouncing off the surface before escaping to space. Such an atmosphere wouldn't transport heat, it wouldn't create weather, it wouldn't protect the surface from radiation, yet it might still produce detectable spectral features if the molecules are concentrated at high altitude, where transmission spectroscopy looks. Red dwarf stars host a cosmic graveyard of dead atmospheres. Billions of rocky planets orbit these cool suns throughout the galaxy, and most of them probably started with air. Then the stars woke up. Young red dwarfs unleash radiation storms that strip atmospheres away layer by layer until only bare rock remains. This is the M-dwarf planet problem. M-dwarfs are the most common stars in the universe, making up roughly 70% of all stars. Rocky planets around M-dwarfs are even more common. Estimates suggest there could be billions of Earth-sized worlds orbiting in the habitable zones of red dwarf stars in our galaxy alone. But if these planets can't keep their atmospheres, they can't support life. The potential for inhabited worlds across the galaxy plummets. Billions of planets become billions of sterile rocks. GJ486b was supposed to help settle this debate. If any rocky planet around a red dwarf could keep an atmosphere, this one seemed like a good candidate. The initial water vapor detection sparked hope, but the August 2024 paper showing no thick atmosphere revived pessimism. The implications extend beyond habitability. Atmospheric survival affects how scientists search for life. Most biosignature searches focus on atmospheric gases that life produces, like oxygen or methane. If rocky planets around red dwarfs can't maintain atmospheres, scientists should focus their life-hunting efforts on planets around sun-like stars instead. But sun-like stars are rarer than red dwarfs. The number of searchable worlds drops dramatically. There's also a mass threshold to consider. GJ486b, at 3 times Earth's mass, represents the high end of rocky planet sizes. If even this massive world struggles to keep an atmosphere, smaller Earth-sized planets have no chance. Conversely, if GJ486b does have an atmosphere despite all challenges, it suggests smaller planets might also succeed under the right conditions. Venus and GJ486b are twins separated by cosmic distance. Both are rocky planets. Both have surface temperatures around 800 degrees F. But Venus has a crushing atmosphere of carbon dioxide, while GJ486b might have no atmosphere at all. Venus's atmosphere weighs 90 times Earth's entire atmosphere. The surface pressure is crushing, equivalent to being 3,000 feet underwater. The atmosphere is 96% carbon dioxide with clouds of sulfuric acid. The thick carbon dioxide atmosphere traps heat through the greenhouse effect, maintaining hellish temperatures day and night. Venus probably started with liquid water oceans similar to early Earth, but Venus orbits closer to the Sun, receiving almost twice as much sunlight as Earth. That extra energy caused more ocean water to evaporate. Water vapor is a greenhouse gas, so it trapped heat, warming the planet further and evaporating more oceans. The cycle accelerated until all the water was in the atmosphere. Ultraviolet light split the water molecules apart. Hydrogen escaped to space. The water was gone, replaced by volcanic carbon dioxide. GJ486b could have followed a similar path initially, but the red dwarf's ultraviolet radiation would have split the water apart even faster. Unlike Venus, which accumulated carbon dioxide, GJ486b's stellar wind might have stripped that gas away too. Understanding these differences matters because small differences in orbital distance, stellar type, and planetary properties can lead to wildly different outcomes. Venus ended up with too much atmosphere. GJ486b ended up with too little or none at all. Scientists have found atmospheres on hundreds of exoplanets. Gas giants like Jupiter show clear spectral features. Hot Jupiters have atmospheres studied in remarkable detail. But rocky planets are different. Smaller, thinner atmospheres, if any exist at all, harder signals to detect. Until GJ486b, no one had definitively found atmospheric gas around a rocky exoplanet outside our solar system. Finding the first rocky exoplanet atmosphere would prove that the techniques work. It would validate decades of instrument development. It would show that transmission spectroscopy can achieve the sensitivity needed for small planets. But the flip side matters too. If GJ486b turns out to be airless, it suggests rocky planet atmospheres are even harder to detect than pessimists feared. Current technology might not be quite good enough yet. The timeline for characterizing Earth-like planets would stretch from years to decades. The historic significance depends entirely on the ambiguous data. If transmission spectroscopy detected real planetary water vapor, GJ486b enters the history books. If it detected stellar water vapor from star spots, the search continues. Finding water vapor does not mean finding life. Water is necessary for life as we know it. Every organism on Earth requires water, but water alone isn't life. Water exists on countless worlds throughout the universe without any biology. Jupiter has water. Saturn has water. Comets are largely ice. None of these places have life. Biosignatures are specific combinations of gases that life produces and that can't easily be explained by geology or atmospheric chemistry alone. On Earth, oxygen is a biosignature. Our atmosphere is 21% oxygen because photosynthetic organisms produce it continuously. The strongest biosignatures are combinations: oxygen plus methane, methane plus nitrous oxide. These combinations are chemically unstable. They shouldn't coexist in the same atmosphere without constant replenishment. Life can produce both simultaneously. Geology struggles to produce both together. GJ486b's water vapor, even if confirmed to be planetary, has zero biosignature value. Water vapor is completely explainable through volcanic outgassing. It requires no life. It provides no evidence for life. It doesn't even suggest the planet could support life because the surface temperature is 800 degrees F. This matters because media coverage often sensationalizes findings. Scientists found hints of water vapor that might be from a planet or might be from star spots. Even if it's from the planet, it just means volcanoes might be erupting, nothing more. The story of GJ486b is unfinished. Additional observations with the telescope's NIRSpec instrument could definitively determine whether the water vapor comes from the planet or the star. Those observations remain scheduled but not yet executed. When they happen, probably within the next year or two, scientists will analyze the data and publish results. If NIRSpec shows the water is stellar, the case closes. The planet is likely airless and the search for the first rocky exoplanet atmosphere continues. If NIRSpec confirms the water is planetary, even a thin atmosphere counts as historic. Beyond GJ486b, dozens of similar planets await study. Scientists have identified hundreds of rocky exoplanets around red dwarf stars, close enough for detailed atmospheric characterization. The telescope can only observe a small fraction of these worlds during its mission lifetime. The Nancy Grace Roman Space Telescope, scheduled to launch in 2026 or 2027, will join the search. Roman will have different capabilities than Webb, including the ability to directly image some planets. The combination increases the chances of finally detecting the first confirmed atmosphere on a rocky world. Ground-based telescopes are improving too. The extremely large telescope in Chile will have a primary mirror 39 meters across when completed in the 2020s. That huge mirror will collect more light than any previous telescope, potentially enabling atmospheric studies of rocky planets around nearby stars. The ultimate goal is finding life. Every step toward characterizing rocky exoplanet atmospheres moves closer to that goal. GJ486b might not have life and might not even have an atmosphere, but studying it develops the techniques needed to eventually find habitable worlds. Within a few years, maybe sooner, scientists will know definitively whether GJ486b has an atmosphere. They'll know if rocky planets around red dwarfs can survive atmospheric stripping. They'll know where to focus future searches for habitable worlds. The answers will reshape our understanding of how common life might be in the universe. 26 light-years away, a planet either wrapped in steam or bare as the moon orbits its red dwarf star. Scientists wait for telescope time, analyze data, and debate interpretations. The mystery persists, but the search continues. Because somewhere in the cosmos, perhaps on a planet much like GJ486b, but farther from its star and cooler, life might exist. Finding it starts with understanding worlds like this one, learning which planets can keep air and which cannot, building the knowledge and tools to eventually answer humanity's oldest question, are we alone? The answer, whatever it is waiting in the light filtering through distant atmospheres.